is energy. Now, um, some of you guys had different definitions, but I do want to stick to the scientific one for this purpose. And energy is the ability to do work. Yep, totally. Now, ability to do work is a definition for energy. However, I really don't like it because one of the frequent definitions of work is the ability to transfer energy. And if we use the definitions of energy as the ability to do work and work as the ability to transfer energy, suddenly we have a circular set of definitions that really don't explain anything. So instead, I also want us to have a definition for energy that connects to something other than work. And energy is the ability to change your position or velocity. To change position or velocity. Okay. When we talk about energy, there are two large categories of energy. There's mechanical energy and non-mechanical energy. You guys have actually dealt with a lot of the non-mechanical energies already. So I'm going to put a column here, non-mechanical. Okay, the first non-mechanical energy that you guys worked with was thermal energy. So thinking back to the kinetic theory of matter, anybody remember what that was? What was, or at least what's part of the kinetic theory of matter? I mean, it definitely involves some of it, yeah. That's conservation of mass. That's something else. We're looking for kinetic theory of matter. Like 4? I'd be floored if any of you still had those notes. Holy cow, you guys still have those. Okay. All right, so kinetic theory of matter. There are like 3 parts to it. Anybody remember one of the parts? Don't think it was 4? Oh, okay, so it was 3 then. I mean, some of it came back into it, but it would have been chapter 3 then. Anybody at all part of the kinetic theory of matter? Or 2. There are more. There is more. You're right. So, but the part that she said was that all matter is in constant motion. That motion is thermal energy. Okay, so this is the motion of particles in accordance with the kinetic theory of matter. Motion of particles according to the kinetic theory of matter. Somebody remind me, how did some of those particles move? Yeah. Yeah, for like liquids, gases, that kind of stuff. Okay. All right, good. So solids vibrated, liquids slid past each other, gases moved randomly. So we remember now that all those particles are always moving. So that's thermal energy. Okay, the next one up, we've got radiative energy. And this one we're actually going to talk a lot about next month. Radiative energy is the energy of light. Okay, and that can be like infrared light, ultraviolet, visible, doesn't matter, that's radiative. Okay. Following from there, we're going to have chemical energy, which again, you guys actually have already talked about. This is one we talked about when we talked about different types of chemical reactions. And any exothermic reaction that released energy when bonds were broken, that's where we were talking about this one. Okay, so some of the examples of that were if we talked about a combustion reaction, we saw that bonds were broken and heat was released, right? Sounds familiar? Okay. So energy is stored in chemical bonds. And then lastly, nuclear energy. We also talked briefly about this one last semester when we talked about building an atom. And we said you could add or take away an electron all you want to change the charge, right? But if you added or took away a proton, you changed incredible amounts of energy. And that's talking about like the kind of stuff you do in the sun or a nuclear reactor. So nuclear energy is the energy stored within the atom's nucleus. In an atom's nucleus. Okay? So in terms of these types of energy, all you really have to be able to do is identify what they are. So if something's heat energy, it's thermal. If something's energy due to a chemical reaction, it's here. If we're talking about the sun or a nuclear reactor, it's nuclear energy. And if we're talking about light, we're talking about radiative. Good enough? The three types of energy that we're really going to be involved a lot more with are what we call mechanical energies. Mechanical energies include kinetic, gravitational potential, and elastic potential. Because these are the ones we're going to focus a lot more on, we're going to go a little bit more in depth on those. Okay? Good? Okay. So last chapter, one of the first things we did at the very beginning of your notes was write down goals. I'm going to put in our first one here, and that's be able to identify and calculate amounts of individual types of energies. Goal. Be able to identify and calculate different types of energy. The first one that we're going to be able to calculate is kinetic energy. By definition, kinetic energy is the energy of motion. The energy of motion. So if something is moving, it has kinetic energy. If something is not moving, it does not have kinetic energy. Yeah, yes. This is a type of mechanical. Okay. To determine how much kinetic energy something has, we say that kinetic energy is equal to half mass times velocity squared. If you remember back to the kinetic theory that Taylor was just looking up for us, part of the kinetic theory indicated that for things that had more mass, they moved slower at the same speed. That's because if we have the same amount of kinetic energy, they move slower at the same temperature. There. If we have a certain amount of kinetic energy, meaning the same temperature, a larger mass means a slower velocity. Or if we have a smaller mass, we have a higher velocity for the same kinetic energy. Okay. Units for this, mass is in kilograms, velocity is in meters per second, but because it's squared here. So anytime we're writing out kinetic energy, we could write kilogram meter squared per second squared as the unit, or this is equal to 1 joule, which is a J. Okay, so kilogram meter squared per second squared or joule, your choice. They're the same thing. Other units that you may encounter that are still just talking about energy include the calorie, or the erg. What is the difference between it being capitalized? Anybody happen to know? It looks like you had a thought. So a capital C calorie. This is the food calorie, food, and it is equal to 1,000 small calories. So rather than measure your food intake in kilocalories, which is totally what you're doing anyway, we just write a capital C to make it sound like you're not eating as many calories. Okay. An erg is gram centimeter per second, or gram centimeter squared per second squared. It's just a unit of energy. We're probably not going to use it, but I wanted to put it up there because it's absolutely hilarious to say erg. So it's up there. Erg. All right. So that's kinetic energy. So let's say, who am I going to pick on? Say a tear. When it's loaded. I mean, I'm right?
I've never seen you work on that.
We had this conversation earlier. A tear is running at, let's go 7 meters per second. If he has a mass, I'm going to go 70 kilograms of, I'll let you convert. Of 70 kilograms, how much kinetic energy does he have? How much kinetic energy does he have? If you don't already have one out, get out a calculator. This problem. First thing you're going to do to solve this. Right? Good. Mass and velocity. Mass is 70 kilograms. Velocity is 7 meters per second. No, because it's a velocity. That'd be an acceleration. Okay? So, plugging this into our equation, kinetic energy is equal to half mass, which is 70, velocity, which is 7 squared. So that's where it actually gets squared, is in the equation. Okay? So all I've got to do now is solve. Times 49. Say again? Yeah. So the kinetic energy he has is 1,400. No. 1715 is what you should get. 1715 joules. Okay. Okay. The tear has energy. Good. What part did you miss, Maddie? All right. So next up, gravitational potential energy. Potential energy. This is the energy something has due to its capacity to fall. The energy an object has due to its capacity to fall. So the further it can fall, the more energy it has. Calculated as gravitational potential energy, GPE, is equal to mass, gravity, height. Mass is in kilograms. What's G? We've been working with it for a couple chapters. Gravity, which would be how much? 9.8 what?
No. Newtons. No, I don't know.
I liked where you started to go. No. Meters per second squared. There we go. Remember, gravity is an acceleration. So it's in meters per second squared. 9.8 was right. But meters per second squared, and then height, meters. So I'm just going to compare what we just wrote to what we've got up here for kinetic energy. Kilogram, meters, meters squared, second squared. So the same thing, right? People see that? That this line and this line are the same? Okay. Meaning that gravitational potential energy is also measured in joules. Hint, all energy is measured in joules.
Or
Meters squared per second squared. Yeah, don't do that. Okay. All right. So let's go ahead and do an example here quick. So we've got, let's say, a pot that is sitting on a windowsill because that is totally a safe place to put them. And then Matea comes over and she bumps the pot. Let's say this pot was 10 kilograms. It's full of dirt. And it's sitting up, let's go all the way to the ground there, 10 meters above the ground. It's a pot. Yeah, she's inside.
how is that flower so good? I can't draw.
Okay. So, we want to figure out how much gravitational potential energy does that pot have before it falls. To find that out, what's the first? Actually, let me write down the problem here. How much?
So would it still be, would the equation still be 1/2 mass velocity?
No, that's kinetic energy. Gravitational potential energy is this one.
I thought you said they're the exact same thing.
I said the unit is the same thing. Okay, so gravitational potential energy is calculated as mass gravity height. It's not calculated as half mv squared because that's the energy it would have if it was moving. It's not moving yet. It's just about to fall. Yeah, she's going to push it and it's going to fall. She's going to give it a little nudge. Okay, so mass, 10 kilograms. Gravity, well, that's always going to be 9.8 meters per second squared, unless we leave Earth. And height is also 10. So my equation, GPE, is equal to mgh, where we're going to have 10 times 9.8 times 10, and I get what value for my answer? 980 joules. Gravitational potential energy.
What's the MGH?
Mass gravity height.
What is the equation? Yeah, but so you just multiply them together?
Yeah.
Wait, what?
There, a parenthesis that I didn't put another parenthesis to, so I squiggled it out. That's nothing. All right, so 980 joules. So we can say that, looking at this one above, a tear running at 7 meters per second has more energy than a pot that's going to fall out of a windowsill. Okay, this doesn't seem terribly useful. Okay, we can say how much energy something has, but that really doesn't do a lot for us. We saw this similar problem when we talked about momentum. If we talked about how much momentum something had, great, who cares? Why was momentum actually useful? How did we make momentum actually useful? Okay, we needed to calculate things. What kind of things? Yeah, we use it to calculate velocity, but what property of momentum allowed us to calculate velocity of things? Question is, what property of momentum made it actually useful for us when we were looking at collisions? What were some of the properties about momentum? I'm not asking variables. I'm asking what property about momentum or what trait about it. Okay, it was a vector unit, you're right. Not really what I'm looking for. Anybody else got a different guess? No? What did you do in every momentum problem? Like, what was part of the solving process? Trying to delve past spring break here. So what property of momentum made it useful for us? Destroyed. So momentum was conserved. Without momentum's conservation, we really could probably care less about it. Okay? But it was because when we looked at a before situation and summed up its momentum, and then we looked at an after situation, the momentum was always the same total. Energy does the same thing. That brings us to our second goal here, which is to be able to show conservation of energy and use it to calculate values or predict values. Goal to explain conservation of energy and use it to predict values. There are two. Hey, last time you got three. This time I've only given you two.
So far, no.
Okay, so with that, conservation of energy.
Whoa. I'm not done with that. Writing down the wrong sentence.
What was conservation of momentum one more time?
Cannot be created or destroyed.
Can't be created or destroyed. All right, so we'll start this one out the same way. Energy cannot be created or destroyed. Momentum could do something, though. What could it do? Could be transferred. Good. So energy can be transferred, but more significantly, it can change forms. But may change forms. All right, so what that's saying is that if I take all my energies at one point in time, kinetic energy at point 1, plus gravitational potential energy at point 1, plus whatever kind of energy you want to come up with, the sum of all those is equal to the kinetic energy at the end, plus gravitational potential energy at the end, plus whatever else kind of energy happens to be there. Okay? This is a useful thing for when we're talking about, say, well, really anything that's turning one energy into another, especially for examples like theme park rides. Theme park rides have to focus on conservation of energy in order to figure out how fast things are going to be moving at different points in the ride. One of the greatest examples for this is simply a roller coaster. Let's take a roller coaster. We'll put a couple of people in it. And here's our hill. I mean, roller coaster, minecart, is there really a difference? A, and let's put this spot at B, and let's say point A is 20 meters above the ground, point B is 5 meters above the ground, I'll move it up. And let's say the people and the minecart have a total mass of 900 kilograms. I mean, it's a minecart.
Do I have to draw that?
And we've got at least 3 people in there, you know, depends. They could add a good amount. All right, so looking at this scenario, what kind of energy do the people have at the top of the roller coaster at point A?
Are there little circles on top of the head?
Yeah.
Does this have to do with Earth?
No, that's just type of energy. Okay, so it probably has a little kinetic energy. How many of you have ridden on a roller coaster? Good. At the very top of the first hill, do you move very fast? Not really. I mean, you're crawling forward. Eventually you start moving, but not really here. So yeah, there's a little bit of kinetic energy, but we're going to count it as almost zero for the purpose of this problem. What other kind of energy could you have here? Those are types of friction, not types of energy. What kind of potential? Gravitational potential, absolutely. So at point A, we're going to have gravitational potential energy because the cart could fall, right? So I'm going to say GPE at point A. Good. Point B, what kinds of energy do you have? You're going to still have gravitational potential because you could still fall further, right? So I'll put equals GPE at B. Any other kind of energy? There will definitely be kinetic plus kinetic energy at B. All right? So in terms of the mechanical types of energy, that's what we've got. Okay? Based on what's here, I can actually now figure out how fast we're going to be moving in this roller coaster. So GPE at A, remember gravitational potential energy is mass, gravity, height. So mass, 900, times gravity, well that's 9.8 because this is an Earth roller coaster, times height, 20, equals gravitational potential energy at B. What's the mass going to be? Yeah, unless somebody bails out, this isn't changing. 900 times 9.8 times our new height of 5 plus our kinetic energy. Kinetic energy is half mv squared. So half mass, which is 900, velocity squared. All right. From there, you guys should be able to figure out how fast this roller coaster is going to go at point B. Take a minute, grab a calculator, figure out how fast it's going to go at point B. So, next question for you. You're at your roller coaster. You're up next to getting onto the coaster. You look down the line either towards the back or towards the front. Who do you hope you're going to see is also getting onto the roller coaster? Your friend, okay, that would be ideal. Then you don't have to wait for them. It depends if you want it faster or slower. What if you want it faster? Bigger people, lighter people? Bigger people, heavy? All right, so when you're looking back left and right, you're hoping to see bigger people. So let's take a look. I want to know if we change this from 900 kilograms, let's just double it. Let's go now and put in like the front line or the lineman for the Vikings or something. Or sumo wrestlers, all right, works for me. Now we're going to swap it out to 1,800 kilograms. So we've doubled the weight in this roller coaster. I want to know how much faster are they going to go at point B. Take a minute, see if you can figure out how fast this group is going to go. Like your answer? No. Being 17.1 meters per second in both situations. Questions about that? So did I even need to tell you the mass? No, I didn't. Next question for you guys. Taking the rubber band ball, holding it right here above my desk. Does it have gravitational potential energy? Okay. How could I figure out how much gravitational potential energy it has? Weigh the ball. How high it is off the desk, the ground? Okay. But what if when it hits the desk, it then bounces to the floor? It's kind of like point A and B, yeah. So it's kind of like saying it drops to the desk, but it could still drop to the floor. What if I got a jackhammer and drilled a hole through the floor here and then went down to, the ground? So where do I actually say this is 0? Because, this is 5. That's 20. What if this roller coaster goes down like here? And then eventually down here? But doesn't there have to be one spot that I say is 0? How do I know this isn't the bottom? Okay, anybody else have a thought? So The answer is we pick 0 to be whatever's easiest for us. Let's take a slightly different look at the same problem one more time. So, right, your lowest spot is just going to be 0. Let's take a look at this roller coaster. How far does the roller coaster drop from point A to point B? So what if we said this was 0? What if we said point B was 0? So now I'd have 900, because really we can pick whichever mass we want to use, times 9.8 times my new height of 15, right? What kind of energy do I now have at point B? What kind of energy did I always have at point B? Well, but I don't have any more gravitational because we just said this is 0. So I have kinetic. So kinetic energy is half mass 900 v squared. Do I have any other kind of energies here? No. So if I were to solve this for V, what do you want to bet that I get?
17.1.
Yeah, go. Yep. All right. I'm still going to get 17.1 meters per second. So one of the things about working with energy is when we are talking about gravitational potential energy, we pick 0 to be whatever height is most convenient for us. If we want to say the ground is 0, say the ground is 0. If you want to say the lowest point you're going to reach is 0, say the lowest point you're going to reach is 0. If you want to dig a 10-foot deep hole and call the bottom of the hole 0, okay, go for it. But really, we can pick whatever 0 is most convenient for us. For GPE, pick the height of 0 to be whatever is most convenient. That would have been nice to know before we did that problem, because this looks a whole lot easier than this does. I mean, it's not terribly different, and the math comes out exactly the same, but it's just a few less steps that we have to worry about. Questions on this one? I mean, read chapter 15, section 1. You don't really have to, but this is what it is. I knew you wouldn't anyway.